this section, we're going to be discussing representations of functions as power series. So there are two viewpoints that we can take on power series. Let's first think about the viewpoint that we had in section 11.8. So in our previous section, we were starting with a power series. So we were given some kind of power series, some sum of Cn x minus a to the n, and we talked about finding its sum, that its sum was equal to some function, and there would be some interval of x's for which the sum was equal to that function. So for example, we looked at the sum from n equals 0 to infinity of x to the n and found that it converged for the absolute value of x less than 1. So its sum was some function f of x. For that particular series, we were able to actually find the particular function, that it was actually 1 over 1 minus x. So we could say that we had our sum here of x to the n was equal to 1 over 1 minus x. Some other things that we looked at the sum of x to the n over n factorial and found that it converged for all x. So its sum was going to be equal to some function, okay? And it actually turns out that this function is e to the x. And this is a fact that we'll actually prove later. Okay, but the main idea here is that our previous viewpoint was to start with a power series and then think about that power series converging to some function and maybe being able to find what that function was. In this section, in section 11.9, we're working sort of the backwards problem. We're starting with a function instead of with a power series and trying to find a power series representation of that function. So why would we want to take a function and then write it as what seems maybe initially like something messier, like this infinite power series? Well, power series representations are really useful in several situations. One use will be in integration, to do some sort of numerical integration when we can't do our typical integration techniques. We can represent our function as this power series, and then we'll be able to see that we can integrate the power series. Power series representations are really useful in solving differential equations, and also for doing approximations of functions by polynomials. So that would be by like the first several terms of our power series representation. So here's a couple of examples of cases where we're starting with the function and trying to find the power series representation. Take this example here of a function, 4x cubed minus 2x squared plus x minus 1. Any polynomial is actually its own power series representation. So here, this function is actually equal to exactly its power series representation, which would just be the sum of those four terms. If we take the function 1 over 1 minus x, okay, then we can say that that function is equal to this power series representation. So it's the same thing that we said above, but we're just thinking about it from a different perspective. I'm saying, okay, I have this function 1 over 1 minus x. I want to write that down as a power series. It turns out to be equal to this power series. That's this sum from n equals 0 to infinity of x to the n. Okay. This also means that I could do approximations of like my 1 over 1 minus x by the first several terms of this power series. For example, I could say that 1 over 1 minus x is approximately 1 plus x squared. Okay, something like this, and of course the approximation gets better and better as I add more and more terms to that. So depending on what I wanted to do with 1 over 1 minus x, maybe this would be a good enough approximation. Okay, you'll see later that we'll answer questions about errors in doing approximations like that, like we did with estimating errors in estimating sums using like our alternating series estimation theorem or integral estimation theorem. There will also be an estimation theorem later for estimating or approximating a function by the first so many terms. Okay, and then we could also think about this from the perspective of our function e to the x. It turns out that e to the x can be represented as this power series. Okay, so just a different perspective that we're taking in this section. We're starting with a function and thinking about how I can write that function as some sort of infinite series. Okay, so this is actually a really big question. Okay, we have a general question of how can we find power series representations in general. Do all functions have power series representations or only certain kinds of functions? And those are some questions we'll answer in the next section. So for now, what we're focusing on, or what we will focus on, is what tools we can use if we have a certain power series representation to start with. And the thing that we do know for sure at this point is that 1 over 1 minus x equals the sum of x to the n for n equals 0 to infinity, okay, where x in absolute value is less than 1. So we want to say, given this information, what other kinds of series can I create? Okay, so it turns out that I can do these 3 different kinds of things to my function and to my series to create new power series representations for additional functions. So one of the things that you'll see us do a lot is we can do certain kinds of manipulations, like I can replace x with something, do some kind of substitution to find a power series representation for something like 1 over 1 plus x squared or 2 over 1 minus x cubed. Something where I can manipulate my function over here and then manipulate the series here to get a new series representation. We're also going to see that I can differentiate and integrate my infinite series term by term. So I could differentiate this function and differentiate the series to get the series representation for my derivative. I could integrate this function and integrate this series to get a series representation for the integral. So let's look at how we're going to go about doing that differentiation and integration. It's actually quite nice that the derivative and integral tools are going to work the way they do. So this theorem just says that if we have a power series that has a non-zero radius of convergence, okay, so that means that it converges beyond just being convergent at the center. We have some interval around the center where the power series converges. Then that means that our function that's equal to that power series is differentiable, okay, which means it's also continuous on this interval around the center of our power series, okay, and this is saying that the derivative of our function is equal to the derivative term by term of our series. Okay, so if we have this sum of Cn x minus a to the n, the derivative then will be the sum of n times Cn x minus a to the n minus 1. So we're exactly just doing the power the power derivative rule on each term in the infinite sum. We can also do an integration term by term. Okay, so I can integrate my power series here, and I'll have my constant of integration plus my sum of Cn, which are just constants, so those just stay the same in both our integral and our derivative. And then this, for the integral, I have my power antiderivative rule, x minus a to the n plus 1, all over n plus 1. Okay, so in terms of radius and interval of convergence here, whenever we take a derivative or take an integral, the radius of convergence does not change. Okay, so these still have radius of convergence r. Now the interval of convergence might change a little bit. When we take the derivative, the interval might become smaller. When we take the integral, the interval might become bigger. So something different might happen at the endpoints, but the radius of convergence will remain unchanged. Okay, and this is just some additional notation saying what we're doing. This is saying the derivative of the series of the sum will just be equal to the sum of the derivatives. Okay, so this is exactly what the theorem is stating above here, that I'll have this sum of n times Cn x minus a to the n minus 1, and that when I would do the integral here, I'd end up with this sum Cn x minus a to the n plus 1 all over n plus 1 plus that constant of integration. Okay. So what we're going to see in several examples is that we can start with this power series representation that we know. We know 1 over 1 minus x equals this sum from n equals 0 to infinity of x to the n. And we're going to be able to use these tools of substituting something for x or multiplying our series by something, as well as differentiating or integrating the series to create additional series representations for new functions. So keep watching to see some examples of implementing these different tools.